All right, welcome, Chapter 11. Finally there. What we're going to be talking about in Chapter 11 is limits. So it's a great topic to be jumping into for calculus if you're taking that next year. So in this section, we're going to learn about limits. We've already discussed the thinking behind them, and we'll talk about where we've sort of seen something that has the similar mindset, but we haven't exactly formally introduced them yet. So a limit uses a similar way of thinking as asymptotes, in that what we want to consider is the value that we're approaching, but we never reach. So if you think about all those times in which graphically we've been graphing asymptotes, what we've always been saying is the function is getting closer and closer and closer and closer and closer to that, but never reaches it. And that's what we're going to really be talking about in limits. Now, sometimes the value that you are approaching is something that you do reach. But the more interesting cases are the cases where it's not. So let's define a limit. A limit, if f of x becomes arbitrarily close to a unique number, L, as x approaches c, so just as x approaches some number from either side. Now it's important that it has to be from either side. The limit of f of x as x approaches c is L. This is written as, and pay attention to how I read this, the limit as x approaches c of f of x is equal to L. And again, what this is saying is the limit as x goes to some number on the function is equal to some value, some numerical value. So, for example, if we had the limit as x goes to 3 of 2x plus 5, if we looked at evaluating this function at 2.7, so if I substituted 2.7 into this, I would get 10.4. If I substituted 2.8 into this, I would get 10.6. If I substituted in 2.9, I would get 10.8. If I substituted, now just working from the right side of it, 3.2, that would give me 11.4. If I substitute 3.1, that would give me 11.2. And if I substituted in what the limit was, I would get 11. So when I look at this, the limit as x goes to 3 of the function 2x plus 5, well, I can substitute that straight in for x, and what I get is 11. So that is my limit, because that's what the function value is, and that's what I'm going towards. Graphically, if you look at this, when I go to the x value of 3, my y value here is 11. And that's, again, the limit because I'm coming to that from both sides of this. All right, so moving along, some limits are found by simply plugging in. I don't like that terminology, or substituting, which is just what we did in this past one. All we did was substitute it in. Now, it's not usually that easy. That's not fun. Oftentimes, though, the function is undefined at that particular point. So for example, if I looked at x going to 2, so the limit as x goes to 2 of x squared minus 4 over x minus 2, when I substitute 2 into these x's, I would get 0 over 0. Well, that's an issue because that is undefined. So I'm not able to figure out like, hey, what is the value of the limit there? And that's what we really want to pay more attention to. That's what's interesting. That's what's fun about limits. So again, notice that if we evaluate this at 2, we get an undefined number. However, if we look at the graph of that, so if I were to just go into my graphing calculator, type in this function, I would get this equation. Here, f of x equals x squared minus 4 over x minus 2. If I go to x being 2, I know that there's really a hole in this graph. The calculator isn't going to show me that hole, but if you do graph this, if you wanted, you can hit trace and then 2 and enter. And you're going to see on the bottom of the screen x equals 2 y equals, and it won't say anything because there is no y value at 2. But there is still a limit because the limit isn't actually concerned with what the value of the function is. It's concerned with what am I going towards. Well, as I move across this graph from the left, and as I move across this graph from the right, I am going to the same y value, 4. And that's what makes the limit here 4. The limit would be 4. And that's again because theoretically, in air quotes, it does pass through 2, 4, but really there's a hole there. If I wanted to look at a table of values to see that, I would see that at 1.9, I get 3.9. At 1.99, I get 3.99. Here I get 3.999. Here I do not get 4. I get undefined. Here I would get 4.001, 4.01, and 4.1. And again, looking at this table, I can see that from the left I'm going towards 4, from the right I'm going towards 4, but I actually sort of jump right over 4. But the limit is still 4. We're going to skip this. We'll do it in a short example video. Does the limit always exist? Now, if you've watched Mean Girls, like I have, you know that the limit doesn't always exist. Lindsay Lohan, not to give a spoiler, but she saves the day by answering that the limit does not exist. It doesn't always. If I were to look at this graph, f of x equals 1 over x, and I want the limit as x goes to 0. You are going to have to add in these words. I apologize. That graph was right on top of those words, possibly for you, depending on what year you're watching this video. As x is going to 0. So if I move from the left of this graph, and as I move from the right of this graph, I am not going to one consistent y value. This function is totally unbounded. Here, I'm going towards negative infinity because I'm just going to continue plummeting eternally. Here, I'm going towards positive infinity because this will keep increasing, or sorry, I shouldn't say increasing, it will keep rising eternally. Meaning that as we approach 0, the function approaches infinity. So when we talk about the function being unbounded, we're saying that it's approaching infinity, or negative infinity. So here, the limit does not exist. Does not exist. All right, moving along, cruising through. What situations make a limit not exist? So we've got 3 situations. 1, if f of x approaches a different number from the right side of c than from the left side of c. So if I'm talking about like the limit as x goes to 2, if on the left I'm going to a different value than I am on the right, then the overall limit does not exist. If f of x increases or decreases without bound as x approaches c. So in this case, the previous one, this is decreasing and sort of increasing or rising without bound. So it doesn't meet that second condition. It also doesn't meet the first condition in the first place. As I move from the left and as I move from the right, I'm going towards different values. The third would be if f of x oscillates between 2 fixed values as x approaches c. So you'll see a little bit of these oscillating functions and how the limit doesn't sort of exist there. A sort of classic one to think about is sine, cosine. They continue to oscillate. So there are some limits that I can talk about for that, but some that I can't because of that oscillating nature. So for instance, if I talked about the limit as x goes to 0 of the sine of 1 over x, so here I have this graph. So what you have here is a graph, and it's really tough to see what's going on here. And I've tried actually like playing with the calculator to zoom in more and more and more and more and more, but you're not actually going to be able to see clearly what's going on here. Here, your limit does not exist. What you're doing here is you're constantly oscillating between two values, but you're never actually going towards zero. It looks deceivingly like it is going towards zero, but it is not. It's just bouncing between two values, those values getting closer to zero, but there is no function or time in which it's going to quote unquote pass through that. Sort of a weird case, a fun case. So we're going to skip this side. We'll do that one in the examples. That's a fun one. Now, what we want to talk about is all the properties. And I'm going to warn you, notationally, this is going to look sort of like disgusting, but it's not that bad in actual practice. So if B and C are real numbers and n is a positive integer, so B and C are real numbers, n must be a positive integer, the limit of x goes to c of b is just b. So to think about what we're saying here, we're saying something like the limit is x goes to 3 of 5. Well, there's nowhere for me to substitute that 3 in. There's no x here. This is just a constant function. So the limit would be that constant. The limit of x goes to c of x is c. And again, this is that idea of substituting in. If I took this c and substituted it into the function, I would get c. So if I said the limit is x goes to 5 of x, well, I substitute that 5 in, I get 5. So that's the limit. The limit is x goes to c of x to the power of n, where n must be in positive integer, is c to the n. And you can see that again just by substituting in. And the limit is x goes to c of the nth root of x, where again, n must be a positive integer. So we're talking about square root, cubic root, fourth root, fifth root, so on and so forth, is equal to n root or nth root of c. Again, just substituting that in. All right, and then we have some more fun ones. No, messy notation. If b and c are real numbers and n is a positive integer, so same conditions here, but if I told you that the limit of x goes to c of f of x is L, so I know the limit is L, some number, and the limit as x goes to c of g of x is k. So for the f function and for the g function, the limit exists and it is a numeric value. Then the following properties must be true. The limit as x goes to c of b times f of x is equal to b times L. And what you're really doing here is saying this b, that is just a constant that's getting multiplied by the function. So you can sort of take that out. And then you just have the limit of f of x, which is L, times b, so b times L. The limit of x goes to c of f of x plus or minus g of x is L plus or minus k. So you're not like distributing the limit here, but you're taking the limit of f of x and then separately taking the limit of g of x. So you'd get L and then plus or minus k. It's not distributing because the limit isn't actually a thing. It's not a numeric value. I can't multiply it in. It's sort of like an operation. The limit as x goes to c of the product of f of x and g of x. So if I'm multiplying two functions and I know what the limit of each of them is, I can simply multiply the limits, L times k. And that would give me the limit of the product of those functions. Same thing happens with the quotient. If I know the limit of f and the limit of g, and I want to know the limit of the quotient of f and g, I can take the quotient of the limits. And same thing happens with the power. If I want the limit as x goes to c of some function raised to an integer value, I can take the limit of that function and then raise that to the integer value. Okay, having fun here. These examples are just going to be examples that we do in the examples video. This is, a super important slide to watch, and then just some more examples. So that's it for the notes. What you want to summarize here, and just hear me out really quickly, limits from a graphical perspective, limits from a table perspective, and just the overall idea of what a limit is. It's what I am approaching. It's not what the function is equal to necessarily. It's what I'm getting closer and closer and closer and closer and closer to from the left and right. All right, thanks for listening. Go watch the examples.